Also in the CITA national community, where he's hosted CITA national fellows. After this place on the CITA council, director, and now happily he's the interim director of CITA. This research program, it's a broad one. Let's say that it starts with the gravitational instabilities in molecular clouds and ends up in the protostars, the jets, the whirling disks that have become actually accessible to us over his career. And he's been very successful in that and brave enough to become an expert in what the role of magnetic fields is in all of this. So let's welcome Shantanu and look forward to his talk.
Thank you, Peter. Very nice introduction, very kind. Thank you, everybody, for coming here today. It's an honor to give a talk to the PAA. Good to be with you all. I'm really enjoying my time in Toronto. Let me say you have a wonderful group here. I mean, collectively among the different units across campus. The density of brilliant minds here is really stunning. It's really amazing. It's really great. I'm sure you all enjoy being here. And so I'm happy to be here at CITA. And I'm going to bring you up to date with some things I've been doing with my collaborators and students in the last few years. This is a problem of star formation, gravitational collapse, a problem which I've been on and off involved in for many years. And I think, as many speakers will tell you, we live in an exciting time. This is the best time because we have both fantastic ability to have observations, high resolution and sensitivity of star-forming regions, as well as the ability to model all the wonderful physics, or at least a lot of it, that we've been wanting to do, but perhaps weren't able to in the past. So definitely thank my collaborator, Masahiro Mashida, who's on most of the projects I'll show, and my various students who I will introduce as we talk about their work. So yes, I'm showing my age. So I came of age in star formation not too long after these classic initial models in the 1970s and 80s, which started out in a very practical way and actually very intuitive and analytic way. If you're going to form a spherical star, you may as well start with a spherical protostellar object, right? So spherical collapse was very much in vogue in the late 1960s and throughout the 1970s. And you had this basic picture of some prestellar dense ball of gas, more or less isothermal at these low densities. And it would collapse until you formed a central object that was opaque. That was your initial protostar, and that might then contract further through some pre-main sequence track into a protostar, into a star. And it was known that there are large-scale magnetic fields. So you had this picture that, yes, it wouldn't exactly be spherical. So you'd have a magnetic field inherited from the large-scale field of the galaxy, and that might be pushed into an hourglass configuration through magnetic flux freezing. And eventually you get some kind of flattened object that might be flattened along the axis of the hourglass. There are reasons to think that the rotation axes and magnetic axes would align, at least roughly, during the initial stages. So most of the modeling had the rotation and magnetic axis aligned. So this was a kind of a toy model picture supported by some actually very good analytic and numerical models. And so I'm going to take you through a little bit of history, especially for the students. So an important development was in the late 1970s when Frank Hsu published a paper, which was a semi-analytic, a really analytic paper, a self-similar model for star formation. And he had an insight that previously hadn't really been obtained or appreciated. There was a kind of idea of monolithic collapse. You monolithically collapse some object, you get a star. But what Frank pointed out is that you should conceptually think of two different phases. One is the prestellar collapse, before you have a central object. And then once you've got your central object, your opaque protostar, now the problem is one of accretion onto that initially very low mass protostar. The initial mass might be 1,000th of a solar mass. And so just before you created that initial protostar, you built up some density profile, which would be scaling like r to the -2. In fact, if you had perfect isothermality and you contracted through a series of quasi-equilibrium states, then you would argue you'd get exactly this, this profile, sound speed squared over 2 pi gr squared. Now, of course, many people argued in the literature whether it would be exactly that. Of course, it wouldn't be exactly that. There'd be variations from that, and you wouldn't be exactly in equilibrium. But this captured some essential part of the problem, which is that if you have some quasi-equilibrium profile, and then you create a central point mass, you've now changed the gravitational potential near the center. You have a 1 over r squared potential rather than a gravitational field, rather than a gravitational field that smoothly goes to 0 before the protostar. And so now you're going to initiate a free fall collapse very close to that protostar where the gravitational field is very large. And as a layer falls in, the next layer is going to fall in after that, like dominoes, as the pressure support is removed from below. So with the back of the envelope calculation, you could show that this profile, if you then had regions inner parts collapsing and the boundary of collapse was moving out of the sound speed, so the rate at which the radius of infall was increasing was the sound speed, then back of the envelope gives you that the mass accretion rate is sound speed cubed over g. Okay, and his solution is more sophisticated. I'm just giving you the intuitive version. And so, of course, you can argue whether it would be exactly constant or be time varying. That's largely beside the point for what I want to say today, which is that an important point that Frank Xu himself identified is the question that really remains till today. This is a fundamental question in star formation. You can calculate an approximate accretion rate. You can argue whether it's exactly that or time dependent. But the fundamental question of the masses of forming protostars has not been answered by any of the spherical or even later, I would say, gravitational collapse calculations performed to date, including the present one. So nice bit of humility there. And, that was Frank Xu actually was, some of you knew him, very amazing character, a lot of intuition, unfortunately passed away almost exactly 2 years ago. And there's a very nice memorial wall that's been put up by the GIA. So the rate has been calculated many different ways, the rate of infall, but the termination is a fundamental question. And that gets at how do you set masses for protostars. So soon after those kind of calculations in the early 1980s, it emerged that you have powerful outflows that come from the young stellar objects, initially detected by Snell and others through spectral lines. And from the spectral line profiles, you could make up this cartoon character of an expanding shell that could be moving as fast as hundreds of kilometers per second. So that's highly, highly supersonic. Sound speed might be only 1/10 of a kilometer per second. And as more and more evidence emerged, you have this idea that you have not only a jet that comes from very close to the protostar and moves at hundreds of kilometers per second, but there's also a very wide angle wind. That wind actually extends for thousands of astronomical units, certainly in this direction, but also in this direction sometimes, along the equatorial plane of the disk. And, from pre-ALMA era, it wasn't always clear exactly where the launch points were. So again, there's a lot of discussion and debate over the years as to whether the winds are all launched from near the protostar or further away or a combination of the two. So just keep in mind that we're talking about a high-speed jet as well as a wide-angle wind. Could be two different phenomena or could be part of the same phenomena. So now, modern era. Okay, so I got to this part of my career where we actually have all this data now. And we have many, many Great observations of outflows. So if I asked you what were ALMA's greatest hits, even I wouldn't know, the observers would know better, but a lot of you probably know about the rings and gaps seen in protoplanetary disks, class 2 objects. That's a great hit for ALMA, but if you look a little bit earlier stage, ALMA has amazing results on stellar outflows, more than I can even talk about. But for example, Kelly et al. Made some advances in measuring the rotation of the outflow and also therefore identifying the range of radii from which the outflow in this case was launched. They would say the launch point was tens of AUs, at least, maybe 50 AU from the central protostar. Matsushita et al. Actually found evidence of separate low and high velocity outflows launched from separate locations and even at separate times. So that was a very strong indication that it's not a single wind that is seen as both high velocity and low. There actually can be two separate components. And this paper, which I think is often overlooked because it's the only result of this kind so far, Felipe Alves et al. Actually see that the outflow is driven beyond the disk edge. So let's put that and give them their own slide. So this is an intriguing paper because you could use the kinematics to identify where the flow was changing from radial to rotational. And that standoff distance was just over 100 AU from the central protostar. So that's presumably your centrifugally supported disk. But you see a strong outflow that's being launched. This is the schematic of what they think they're seeing. The outflow is actually launched beyond the disk. So this is not the traditional picture where you have a rapidly rotating Keplerian disk. Keplerian means relatively rapid rotation, and maybe you're flinging matter off in a wide angle wind. That may be happening, but in this case, the wind launch is happening outside the Keplerian disk. Okay, so this paper has, it's intriguing, and I'm going to tell you it's really important because I have show you results that are along this direction. Yes, yeah. The spectral line shape would be different, and in this case, you can actually map the actual blue shift, red shift. Yeah, you're actually resolving the outflow region. So another interesting set of observations, not really outflow or not labeled as outflow, is these large arc-like structures on thousands of AU scales. Remember, your initial unit of collapse might be 10, 20,000 AU. That's your dense core. Disk scale, maybe 100 AU. This is intermediate on 1,000 AU scale. What is this? Is this some nasty initial condition? Well, it's tempting to say, well, this is evidence of turbulent initial conditions. But that would not be the most imaginative explanation, right? You can always attribute random structure to random initial conditions. But is there a physical reason why you might expect to see something qualitatively like this emerge out of gravitational collapse? So, okay, yes, and I'll show you later, okay? So back to the star formation rate, infall rate question. As I said, we've been talking about accretion rates for a long time. Star formation is an accretion process. When would it stop? Well, in a numerical simulation, you can say it'll stop when you run out of material in the simulation. But what happens in nature? Can nature actually give you a finite mass reservoir? That's hard to demonstrate. First of all, for many different lines of argument, whether you look on the galactic scale or an individual low mass star forming molecular cloud, only about 1% of the mass has gone into stars. And so you have a very large reservoir that does not ever form stars. And you might argue, well, okay, somehow we keep a lot of the mass from entering the dense cores, and the dense cores will form stars. The dense cores contain only a small fraction of the total molecular cloud mass, but even their masses can be 10 solar masses or more. They're typically nowhere near the average stellar mass of about 0.2 solar masses. So Simple Jeans mass argument will never work to explain stellar masses. And even if you don't believe in genes, you say, well, just look at these dense cores that are observed. Their masses are much too large. And even those masses are often arbitrarily determined because the boundaries of dense cores are hard to identify. If you might do some kind of mapping to identify cores, but you might have some software that will draw nice boundaries around your density peaks, but there's always more matter outside it. So there's not always a clear edge in an observed star-forming core. So since outflows were discovered in the 80s, that was considered a great way out. Outflows, if they're powerful enough, could sweep away a lot of the dense core material and therefore put a stop to accretion. Perhaps the outflow gets powerful enough at some point and stops the infall. But there's always been this nagging problem that outflows are bipolar and much or most of the accretion comes through the equatorial plane. So how do you actually stop infall in the equatorial plane is the big question. Even if you could, let's say you could in the other directions. All right, so magnetic fields were recognized early on as the driving mechanism of outflows. And there's two different mechanisms by which magnetic fields are known to be able to drive outflows. These are two limits, and reality may be somewhere in between. Nice simulation by my former postdoc, Takahiro Kudo, who's now a professor at Nagasaki University. This simulation shows two different mechanisms at work. And the first mechanism is the so-called tower flow, driven by the pressure of twisted magnetic field lines. And so if you set up this kind of thought experiment simulation where you have magnetic field lines, colloidal field lines, and a rotating dense disk, and some lines are white, some are pink because of where their launch points are, where the put point is. The inner lines are in pink, the outer ones are in white. And you can get this thing going with rotation, and because of magnetic flux freezing, you will twist up the field, and the vertical gradient of the twist will then eject matter along the field. And this will, of course, be happening in both directions. You get above and below the plane, so you have bipolar outflows. And so you essentially eject matter. This is a kind of a one-time event. You've got this thing rotating. But if you have infall continuing from outside, you'll keep feeding more angular momentum into the inner region, and you can keep this kind of thing going. But notice one thing, that once this twisted region went up and ejected matter with it, you're left with a low density environment here. And at that point, you've actually transitioned into something more like the magnetocentrifugal flow, which is what you get when you have a very high signal speed. Signal speed in this case is the Alfvén speed, magnetic field divided by square root of density. If you evacuate a lot of material and you get to a low density environment, signal speed is very high. Once the signal speed is very high, you can expect a region to co-rotate with the disk, okay? If I rotate my pen, the top also rotates because the signal speed is thousands of meters per second inside the pen. So with a high signal speed, you can get co-rotation. In that case, you can fling matter off. If the rotation is high enough, the rate is high enough, you can have matter that moves outward along the field lines. I'll talk about that effect more later when I show my results. But the twisted field model works when you have a low signal speed, and then you can just see the disturbance propagating along the field, and then that pressure gradient in the field pushes the flow. All right, let's move on. So when we're doing these 3D calculations, the big challenge is, one of the big computational challenges is that you're facing a kind of a Zeno's paradox. You want to get more and more close to the star-forming region, but the closer you get, the more slowly you have to move in time. Because in numerical simulations, we have something called the Courant condition, suitably modified for magnetic fields, where your time step has to be essentially less than one signal crossing time across your cell. All that means is the smaller your cell, the smaller your time step. So when you get to, if you're trying to simulate in great detail the protostar itself, very nice paper by Vete et al. They put in a lot of physics. The calculation initially went like 100,000 years of physical time. You get to the protostar, and then you can only go one more month before you're just dragged to a halt because you're taking tiny, tiny, tiny time steps. Can't get very far. So time step limitation is a problem. And so for long time scale simulations, we use something called a sync cell, which I'll show. I'll just show you quickly one other model that Masahiro and I published a few years back, which did not have a central sync cell. So you're actually resolving the protostar in this case. You're putting a lot of cells near the center. This model is the furthest anyone's been able to go. It's 2,000 years. That's pretty good. But probably your youngest class 0 protostar that you observe might be about 10,000 years old. So it's still not yet in the observable domain, but many of the features you do observe are beginning to emerge here. You do see a separate low velocity outflow from the outer disk or even beyond. And you see a high-speed jet from the inner region. Okay, the inner region, the strong jet is driven by something like the tower flow I showed you earlier. The outer weak outflow is maybe something a bit more like the magnetocentrifugal flow, but in reality, it's a hybrid. It's something in between. You're never really at one extreme limit or the other. Okay, and yeah, we see some knots in the outflow and all, but that's beside the point for what I'm doing today. We're not going to be talking about jets anymore. I want to talk about the outer outflow. And so if you want to capture the wide angle wind, you need several elements. You need to go far enough in time, which means you want to introduce a central sync cell. So you don't have to resolve anything within some inner length scale, in this case, 2 astronomical units. Once the density in the central cell becomes high enough to be a protostellar density, you start removing mass and putting it into a point mass whose potential you add to the calculation. So now you've added a central point mass. And now you can calculate much further in time because you're not trying to resolve anything within a couple of astronomical units. So no jet. The jet has to come from very close to the protostar. Since it has an escape speed of 100 kilometers per second, it has to come from just a few stellar radii away from the star. So like many of these calculations, you start with an isothermal sphere and you embed it in some uniform outside medium. For simplicity, solid body rotation and uniform magnetic field. There's actually a vast parameter space to be explored in the long run. Each of these simulations might take about 10 weeks. Okay, so it's not something you can do for a very large number of parameters. So there's up to 21 levels of refinement. You're doubling the resolution each refinement. Nested grid is probably the best way to go for this kind of problem if you want to resolve what's happening in the surrounding region. You're not really just interested in the center. In fact, you have a sync cell. You actually want resolution laterally. And so nested grid is good because you got a decent region where you have good resolution. You're not concentrating everything to the center like you might do with a fully adaptive mesh refinement. Okay, that's for your numericists to appreciate. Okay, so let's see, next picture is coming. Not sure what happened. Okay. There we go. Okay, so finally some results. Okay, so this is actually not in the paper. This is the plot that Mahmoud, Mo, or me were looking at and really puzzling over. So this actually is maybe the big money slide in the top. Looked at this and initially, so this is at some time after you formed the protostar, 26,000 years after. So this is the class 0 phase, the embedded phase. All of the results in this paper are about the embedded phase, at least in the first part of this talk. So we formed an outflow. Great. Okay, very happy, right? Okay, you see the red is positive, blue is negative. So you got a bipolar outflow. Protostar is right there. It's about 0.3 solar masses at this time. Great. Bipolar outflow, like we all expect. Okay, so we're resolving it properly, we think. Zoom in, though, to 100 AU. The colors have reversed. Okay, so that means above the protostar you have infall, but further up you have outflow, and just the opposite here. There's something wrong. Is the simulation like, is it CRAP? Is there something you've done terribly wrong? And so, yeah, we really puzzled over this. And of course, what we realized is, yeah, it's one of those conundrums that seems unsolvable, but only if you think in one dimension. So we started looking at what's happening in the larger scale. So yeah, this was actually a lot of fun. This was what we do simulations for. We do them to learn new physics, not just to calculate things you already know in more detail, right? And the best simulations are the ones that show you something new that you initially don't understand, and then you figure it out and learn something. Okay, so what did we learn? So the key is to start looking at more dimensions. You may not want to look at the full messy 3D simulation, though. That's even hard. So our minds are better at lower dimension. So the optimal way to analyze this was to do an angle average, convert from Cartesian into polar coordinates, and look at the 2D maps. Okay, so this is a 2D map of the poloidal magnetic field lines along with a heat map of the magnetic field strength. Okay, strongest field is here. I won't say much about this because this picture's on the next slide too. All right, so this is one of the two money slides again. So this is level 11. So this is at least 6 levels in from the initial sphere. So you've doubled the resolution each time, gone 6 times, 2 to the power 6. Resolution might be about 5 astronomical units here. And this is already showing you that if I'm looking at the magnetic field lines and the field strength in color, that I have a region where magnetic field is being dragged in from very far away from the collapse, from large scale. This is consistent with approximate magnetic flux freezing. This simulation has non-ideal MHD though. That's really important. Okay, so we have ohmic resistivity in the problem, and the resistive coefficient is density dependent. So this region is consistent with flux freezing, but the field lines are straightened out in this region. And if we zoom in, you see that this region has much more straighter field lines, not exactly straight, but this is the region where the magnetic diffusion is dominating. Okay, flux freezing, pinched field line, diffused field line here, straightening out the field lines. Ohmic dissipation is like a diffusion in the magnetic field. And this is the region where the magnetic fields are colliding, if you want to think of it that way. The field lines coming in and the field lines diffusing out. And they meet and create an off-center peak in the magnetic field strength. The magnetic field is decoupling from the gas. The gas is still forming a circumstellar disk. This is a Keplerian disk. It's got this spade-like structure because the vertical gravity gets weaker as you move outward in radius. Once you get outside the disk, you're in what we call the pseudodisk. The pseudodisk is the gas density layer that is flattened along the mean density, along the mean magnetic field direction. And it's actually squeezed by magnetic forces that push it toward the galactic plane. It's much thinner than the circumstellar disk. But the field strength peak is right about here, okay? Maybe here or so, okay? It's outside the centrifugal disk. So that's a new result. So again, this is well into class 0 phase, about 26,000 years with a central protostar of about 0.3 solar masses. Now I'm going to look at the magnetic field plots again, along with the velocity plots. Oops, that's not the one I want. That's the one I want. These are the same 3 plots I had earlier, level 11, 12, 13. This is the poloidal velocity vectors and a heat map of the strength of the poloidal field. So again, okay, this is the most important slide. Okay, they just keep getting more important. So now what you see is that all this region that was pseudo-disk is launching a wind. There's a pseudo-disk wind that actually extends hundreds of astronomical units. Never been observed. but I think it's there. It's weak. It's just slightly supersonic. But as you get toward the main launch point, it's significantly supersonic. It's getting close to, several to 10 kilometers per second. The strongest launch is from right here, where you have the strongest magnetic field. And you can see the blue color here is darkest, actually accelerated. This is the strongest flow. Weaker flow coming from further out. It's a pseudo-disk wind. There's no disk wind. So for people who really believe in disk wind, sorry, there's no such thing, not at this phase, okay? This is the embedded phase, okay? If you really love disk winds, I'll have some better news for you later in the talk. But at this phase, it's a pseudo-disk wind. Your main launch point is where the magnetic field peak is. The density is still peaked at the center. Magnetic field is peaked off center due to dissipation and diffusion. The disk itself is here, here, here. It's not only is there no disk wind, the disk is actually receiving infall. The disk is gaining mass. Yeah. Yes, some gas from here is going up and it's in a gravity-dominated flow. It's not moving up fast enough. It actually gets captured by.
The magnetic field is too weak to do much.
That's right. That's right. Yeah. So this kind of thing, it's the first time seen in any simulation like this. I mean, obviously, if you look at, say, Blanford-Payne magnetocentrifugal theory, which has lots of simplifying assumptions, even there is a regime where you'll have magnetic launch and another regime where if you launch at the wrong angle, you might be in a gravity-dominated flow and fall back to the center. So disk infall, no disk wind. It's a pseudo-disk wind only at this point. And even though it's a weak flow, because of the large surface area, you wind up removing about 1/3 of the infalling mass. So this is where the mass loss and momentum delivery, a large part of the momentum delivery actually happens. The central jet, yeah, it's very fast, but it doesn't actually carry much mass. There's no jet in this simulation. I'm just talking generally. It's this outer wind that really is part of the star formation inefficiency. Okay, I don't have a lot of time, although how long do I have? Till 3 or 3:10? Till 3, right? Okay. Quickly talk about the Alfvén surface for magnetic wind aficionados. The Alfvén surface is supposed to be the surface up to which the magnetic energy dominates the kinetic energy of the flow. Beyond that, the kinetic energy of the flow will dominate. And so the idea is within the Alfvén radius or Alfvén surface, which would be the kind of yellowish orange regions, you can launch by magnetic effects, and you might have some co-rotation, like in the magnetocentrifugal theory. You'll have it's magnetically dominated. You have some co-rotation of the gas with the magnetic field. So these are exactly the launch regions in the pseudo-disk. But once the flow moves up and accelerates, and it goes beyond the Alfvén surface, meaning that the kinetic energy is now greater than the local magnetic energy, you would expect the field line twisting to happen because you're going to wind up the field. And that's indeed what happens. The ratio of B phi over B poloidal becomes large in these regions. So this is kind of consistent with some steady state wind theory. It's not exactly purely magnetocentrifugal launch followed by twisting and tower flow, but there's some elements of it. And as we show in the appendix of this paper, there's nothing sacred about 60 degrees, as in the original Blanford and Payne paper, because that is based on a series of assumptions, like everything moves with the magnetic field, co-rotates with it, moves parallel to the field lines. Magnetic forces are the only force, and you're in steady state, and you're launching from a Keplerian disk. That's built into the Blanford-Payne theory. So clearly no launching not from a pseudo-disk where the gravity is a bit weaker, and you can actually launch from angles larger than 60 from the horizontal plane.
So it's not supported by rotation.
That's correct. There is rotation, but it's not rotationally supported. Well, it's infalling. It's infalling, but it's also rotating. So imagine you're falling in and your rough angular momentum conservation, not exact, you're spinning up, but you haven't spun up enough to hit centrifugal equilibrium.
That's why it's called pseudo-disk.
Yes, yeah. So it's actually infalling. And so if you're in the rotating frame, you have centrifugal, you have magnetic pressure, you have gas pressure, but gravity is still dominating. Okay, yes, right.
What's the evolution of the specific angle moment of the material?
It's more or less constant in the pseudo-disk region. In the equatorial plane, it's like pretty much flat. Okay, a little bit of mass, but
And where from there?
then in the disk it becomes something like flux. So think again, momentum versus radius, and increasing and declaring this. And then it becomes flat. Yeah, there's a figure in the paper. You can look it up. This is interesting. I'm going to do it in passing because this is not exactly steady state like standard wind theories. The dashed line, which is magnetic field line, and solid line, which is velocity vectors. From the previous plot, you might have thought they're aligned, but they're not actually. Okay, there's a systematic offset, which we are actually investigating further now, but there's no reason to think in this kind of model that they would be aligned for many reasons. But number one reason is the gas is infalling. All steady state models that assume that these are parallel are in static disks in the radial direction. They're not collapsing. So it's a collapsing flow. And so there's definitely some field line dragging going on, and it's a more complex situation than any of the standard steady state models. But I think there's enough elements that we can still understand it, right? In terms of driving by twisted field or magnetocentrifugal launch. Okay, so that was the main result I want to share with you. A couple more things. I haven't actually talked about the arcs and rings. I know it's in the title, but so we'll get to it. So you see things like this. If you try and infer the magnetic field structure, sometimes you see interesting things like this. This observation by Enric Bartho et al. Naively, you expect hourglass pattern. If it's a dust, I'm not going to go into all this, but dust polarization is a proxy for the local magnetic field direction. So you can get a magnetic field direction from dust polarization, and then you make a map of inferred magnetic field lines. Sometimes it's not an hourglass, but it's an interesting pattern. It's not random. So this is a case of, the inverse problem is of looking at something at a funny angle with radiative transfer can give you all kinds of results. I'll quickly deal with this magnetic field issue. This is really a separate talk. This is with Xiwan Li and Gianfranco Bino, my former students. Xiwan is now a PhD student at Chinese University of Hong Kong. Gianfranco is working here in Toronto at State Street Financial. He's a quant. But this paper was written after he started the job. His PhD papers were before, separate. So he's still able to do work as a quant. So I'm very, very impressed by that. And I should mention Mo, who I showed earlier, he's assistant professor at Al Ain University in UAE. So he's teaching lots of students. Yeah, challenging, right? But doing good. Yeah, so here what we're showing is a kind of an analytic model of the kind of magnetic field you get in these collapse calculations. It's kind of an hourglass pinched with the pseudodisk, but you also have a toroidal field. You normally think you're looking at these at 90 degrees to the magnetic axis, but if you tilt it to 60, then it looks more complicated. A little bit more complicated if you do a field line map, but if you run it through radiative transfer and get the dust polarization, I'll just quickly point out, when you look at some arbitrary angle, say 60, you can get all kinds of patterns in the polarization directions as well as the intensity. that are very counterintuitive. And basically, it's like when you're not looking at it like that, you're looking at the magnetic axis like that, all kinds of patterns are possible. They're not random. There is some order to it, but they're nothing like an hourglass. So that's an interesting point to keep in mind. So the earlier result was the class 0 phase. So we actually then later ran another model to just beyond class 0 phase. So into the phase where nearly all the matter is now in the star disk system. It's either gone into star disk system or it's been ejected in an outflow. So you get to pass the embedded phase, something you might call observational, you might call it late class 1 or class 2. So at this time, in this simulation, relatively early, 70,000 years even, you do finally get a disk wind. Okay, so we're all disk wind lovers. Yeah, it actually still does exist. And it exists only when you've blown out enough of a cavity that the pressure differential between the disk and the surrounding medium will drive some ablation into the external medium. But this is more like the last gasp of mass loss due to pressure difference. This is not the phase where the star is really being assembled. In the earlier pseudo-disk wind, that's when you're entraining a lot of material and moving it out. You're entraining dense core material and moving it out. This wind is not doing that. This is just a kind of an evaporative or, flow of the residual mass, some residual mass from the disk. This is a way to disperse the disk. This is not a way to entrain matter in the envelope and send it away. So a disk wind does finally exist. So we're not being so heretical. I guess people who love disk winds could still. Not in this case, no. Yeah, sorry, evaporative is not the right word. Yeah, ablation or whatever. This is driven by pressure difference. Yeah, thanks. So at this very late time, probably the most interesting thing is if you look at the equatorial plane, you have the infall, but you have a region of outflow in the equatorial plane. This was not because of a bipolar outflow. This is actually outward motion due to gas and magnetic pressure. And the explanation in the end is simple, that you've got so little, you've blown out so much mass with the outflow, at least a third, maybe more, has been blown out, that the gravitational pull of the inner region is now less. And the magnetic and gas pressure can now actually push some of that residual matter back out. So have we solved the accretion problem? Well, for this simulation, but not exactly, because this is just the last little bit of mass in the simulation. And we have only that last bit of mass left because we had a finite mass reservoir in the simulation. In nature, you have this much larger reservoir, and you have to explain why that's not going to fall in as well, right? You can't just have an isolated box. But still, this is progress, okay? The gravitational binding has been reduced to actually, for the first time, see outward motion in the equatorial plane. Yeah.
This looks fairly axis symmetric.
Yes, the initial condition is axis symmetric. And let me get to the next model, okay? What I'm going to argue is, I don't care if it's highly axis symmetric or not. I'm going to say, even if it is axis symmetric, you should get significant non-axis symmetric structure out of the result, okay? And even though in this case, it wasn't axis symmetric, but not highly non-axis symmetric. But if you start with a stronger magnetic field than those models, the ratio of mass to flux normalized to this value essentially tells you the ratio of magnetic energy to gravitational energy. If this ratio is larger than 1, it's ratio of gravitational to magnetic. So in the previous models, this ratio was 2 or 3. Gravity was dominating magnetic fields in the initial state. That's why it all started to collapse. But you can start something that's more of a standoff balance between magnetic and gravitational, and it'll still collapse if you add non-ideal MHD. So neutrals can always slip past magnetic field lines and initiate collapse, and then they can even drag in the magnetic field. So we have this in this simulation. So collapse still happens, but it happens with carrying along a slightly stronger magnetic field than in the previous models I showed you. And so what happens then is the equatorial plane at different times. Okay, 1, 2, 3, 4, 5, 6, moving forward in time. At some point, because that same effect happens, where magnetic field diffuses out of the center, out of the disk, moves into some adjacent region, if you do that in a strongly enough, and you create a strong enough gradient of magnetic field in that outer region, then something very interesting can happen. What's important really is not the gradient of the magnetic field itself, but the gradient of the mass to flux ratio. If I told you that we set up a situation where we had protostar here, low density here, and high density here, you'd say, oh, that's really Taylor unstable. The high density and low density will exchange positions, right? If you have a magnetic field embedded and you have even approximate flux freezing, then what's important is not the mass density, but the mass to flux ratio. And if I create a situation where I have a lower mass to flux ratio followed by a higher mass to flux ratio, protostar is here, low mass to flux ratio, high mass to flux ratio, those two regions will also want to overturn. And they can only accomplish it through non-axisymmetric motions. So you will naturally, if you at any time, this is some random time, this is the disk region where the mass to flux ratio is declining, just like the density is declining. But just outside, because you're piling up magnetic flux here, you can have, for a short time, an inversion layer where the mass to flux ratio is increasing outward, not decreasing outward like it is on the large scale or inside the disk. And nature doesn't like that. It's going to beat you down to the critical value of 1. This is where gravity and magnetic local pressures balance. And so for most of this region, you're trying to always come back to this critical line, but you're not, sometimes you're above it, and then you get down below it through interchange instability. So this, we would say, is the origin for some of these arc-like features. Okay, can't prove it, but this is a nice proof that just like inside a circumstellar disk, even if you start axisymmetric, you're going to get non-axisymmetric due to gravitational torques. Even on this larger scale, nature will try and reduce gravitational potential energy by moving flux tubes around, and you're going to get this non-axisymmetric structure. We get it for some initial conditions, maybe not for others, but it may be a more general phenomenon than even our simulations are showing. So you've got these outgoing cavities of strong magnetic field. You've got shells of swept up material. You also have some infall coming in along these shell regions. So it's a very complex flow. This is in the equatorial plane. And so this is actually a more dramatic example of outgoing flow along the equatorial plane than I showed you earlier. Earlier, it was just a residual thing at the end. This is very much from the beginning. If you set up conditions for interchange instability, you will have these structures. So rather than put in turbulence by hand, which I would say is the less imaginative thing to do, you might actually find an instability occurs that actually, instabilities are the cause ultimately of something you would call turbulence. And interestingly, in this early phase, if I divide out the mass flux, let's forget the top panel, let's just look at this one, which is a particular level, level 8. These two lines are showing you this is the outflow due to the wind, the disk or pseudodisk wind actually. This is the mass flux from the pseudodisk wind, which is mainly above and below, which is actually above and below the equatorial plane. But this red line is the mass flux due to the interchange instability, which is mostly in the equatorial plane. So at least in this early phase, you have as much mass flux in the equatorial plane roughly as you do in the other directions. Yes,
Are
Chris.
they effectively the same structure?
Yeah, it's all one complex thing. So it is hard to disentangle, but you kind of disentangle it with radial motions versus non-radial motions. Yeah. So it is overall a complex.
In the numerical model, when
Mhm.
you're forming these bubbles,
Mhm.
what is the magnetic diffusion?
The diffusion length.
Well, it looks like these bubbles are very strongly magnetic.
Right. Yeah.
And I'm just wondering how easy it is for matter and field to slip past each other.
Right. Well, ultimately, it's caused by some slippage. So you're expelling magnetic field out to some outer region. In that outer region, the density is less, and so the resistivity is less. So the resistivity is a very strongly density dependent quantity. Yeah, right. And the ohmic also. So both of them undergo a very steep rise of like 10 to the 10 to 10 to the 12 per cubic centimeter. So if you move flux out of that zone, as it gets to that interface, now it's in a more coupled zone. So you're driving magnetic field out of a poorly coupled region into a better coupled one. And so the interchange instability is kind of happening in this better coupled region. And so you can think of interchange instability as the way to remove magnetic flux within the constraint of flux freezing.
So the city is increasing inward.
Yes. Okay, I think I'm almost done. In fact, I am done. Okay, extra slide. Okay, so sorry, I went over a bit. So really, I want to end with the broad brush points that 3D simulations with magnetic field, MHD, non-ideal MHD, can actually teach you new physics. There's a lot of new things emerging. Pseudo-disk wind, interchange instability, those are the two big ones here. And we also live in this wonderful ALMA era where we get new amazing results every year, every few months. So the complexity of observations, hopefully we can keep up with it through the simulations and learn some new things along the way. And I think the equatorial outflows now are a very interesting topic, and that might lead us toward understanding how the accretion finally terminates. Okay, thank you.
We don't have the horns at the door, is that correct?
Yeah, I know.
Good. We had a few questions during, but you didn't interview now before we go upstairs. Bob?
Total ignorant observer question, but I mean, these simulations don't have jets. And is that because, you put that same particle in the center? And then how do you as theorists know that those jets aren't super important? Because when I, as an observer, look at them, I'm like, they're the.
Yeah, no, I mean, they are super important. There's no doubt about it. For lots of things. I was only claiming that for the mass loss, the winds actually carry away significant portion already. They're carrying away a third of the inflow mass already. I don't think the jet can carry away much more.
Okay.
It's not launching from a larger area, even though it's fast.
Okay,
It's a very small.
so if you eventually Moore's law, whatever, eventually you can put the jets in. We already know that it's not going to affect equatorial wind loss and.
But it obviously affects what you see, because what you observe is a combination of the jet and the wind. So much of the kinematic features you'll see might be emerging from the jet itself. And of course, there are models like X-ring theory where it all comes from the inner region. So that's not consistent with what I'm showing, but there are those who will argue it all comes from the inner region. What you're seeing in the right angle wind is some swept up engine, right?
Yeah.
That was the initial interpretation of this now. That's just one thing, and then it sweeps up this big thing. But I think there's a lot of evidence now from observation as well as these kind of models that are separate.
Thank you.
Great.
So with your simulations, do you tend to have a preferred orientation between the magnetic field and the super rotation?
Yeah, in all these models, they're perfectly aligned to begin with. Now, I actually have published other papers where they're misaligned, and so that's another whole direction to go. I mean, you get less, obviously, get more complex structure. You tend to get larger disks because this magnetic braking effect is not as efficient. So you get larger disks, maybe more structured disks, more chance for disk fragmentation. So, yeah, I think, there's definitely a tendency to align the two, I would say, based on theoretical grounds, but there's no reason to think they become perfectly aligned. And so I think, yes, that's ultimately, you would know, it's probably the explanation why you often see the eject directions kind of misaligned.
Yeah, we tend to see misalignment in the earlier stages.
Mhm.
Why is,
Right,
an open
right.
question still, but
Yeah.
the impacts further down the line are really interesting.
Mhm. Yeah, so I think the jet in theory mind, the jet should be perpendicular to the disk, but the disk may not be aligned with the magnetic field. And those outcomes do happen in those kind of simulations.
Oh, well, so maybe that's following up to it. I was kind of intrigued that your concentration point or your real capillary disk is about 40 AU in size, which coincidentally agrees with the ALMA determination of size disks in class 0, 1, 2 sources.
Yeah,
So what's your initial condition that give you 40 AU disks?
yeah, I think it's just taking typical rotation rates that people use for dense cores. You know, so total.
You take this.
Yeah, total, let's say total specific angular momentum budget of 10 to the 20, I think, CGS units, between 10 to the 20 and 21. I think that's the standard average budget for protostar core, specific angular momentum. And it does seem to convert into something like 40 AU. If that all collapsed with no angular momentum loss, it might be more like 100 or a few hundred AU. So there's some order unity reduction due to this magnetic effects of the outflow and the
Okay, so it's a robust because of that.
yeah. So I think that maybe there's something fundamental there that one could probably say that magnetic field and outflows reduce the centrifugal radius by a factor of 2 or 3 compared to the angular momentum conservation idea.
Right.
Now, if we run this model with a different initial rotation rate, you get a different size base, for sure.
Okay, in the highly magnetized example, did you have disk formation there, like actually Kepler support disk in them?
Yes, yes, we did, because we still have magnetic dissipation in the inner region. So you still dissipate a lot of field in the center, so you don't get magnetic breaking carried away.
But it does matter, right, in the sense that the inner part is the part where the dissipated effect is important.
Yes, yes,
So
actually.
it coincides with 40 AU and momentum.
Yeah, I mean, in a sense, we need the disk. Because the disk is a bottleneck to collapse, which forms the centrifugal region. That region is going to grow in density because you're piling up matter, that's right. Once you grow in density, you get to the really high resistivity.
Feedback.
So it is it's a two-way street.
All right, join me in thanking Shantanu for a very